Hello, I'm Seema and welcome to part 45 and the last part of the chapter Hydrocarbons. We have been studying about aromatic hydrocarbons. In this video, I'm going to talk about the directive influence of a functional group in monosubstituted benzene. When we studied the structure of benzene, I told you that it's a very symmetrical structure, a hexagon, a planar hexagon, and all the carbons in a benzene ring are identical. So when you have a monosubstituted product, which means one group or atom that is attached to benzene, for example, here you have the OH group attached to one of the carbons, it forms a monosubstituted benzene, or the monosubstituted benzene is that when one of the carbons has been substituted, one of the hydrogens has been substituted by an atom or a group of atoms in the benzene ring. Now, since all the carbons of the benzene ring are identical, you can get only one monosubstituted product. It is not like if the OH group attached to any other carbon atom, you would have got a different structure. The structure would still be the same because all the carbons are identical. Now, what is the effect of this group, the monosubstituted, the substituent that is attached? It has an influence on the molecule. And what kind of influence does it have? It influences the substitution. If another substitution has to take place, a second group has to attack the benzene ring. The presence of one group or one substituent affects that attack. How does it affect that attack? Before we understand how it affects that attack, let us understand what are the possible positions at which substitution can occur. Let us say that this is the OH group, this is the carbon at which a substituent is already present. So this is monosubstituted benzene. The benzene ring is hexagonal. Don't go by this, it's just a card that I made for explaining some other topic. But we are just taking the hexagonal structure here now. If this carbon, let us say, has a substituent, the second substituent that comes can come here. If it comes here, when you have 1,2 substitution, it is called ortho substitution. You're already aware of this. Yet there's no harm repeating it. If the second substituent comes and attaches itself to the third carbon, if this is carbon 1, if it comes on carbon 2, it is ortho. If it comes on carbon 3, it is meta. It is a meta substitution. If it comes on 4, that is opposite to that, then it is 1 and 4 substitution. It is known as the para position. So, ortho, meta and para position. If the substituent comes and attaches itself here, then you will start counting from this direction. So, the second, if this is carbon 1, this becomes carbon 2, this becomes carbon 3. So, 1,3 substitution would be a meta substitution. And if the second substituent comes and attaches itself here, then this is carbon 1, this is carbon 2. So, this again becomes an ortho substitution. In other words, when the second substitution takes place, or we say when benzene is di-substituted, there is a possibility of 3 possible di-substitutions. One is ortho, the other is meta, and the third is para. There are 3 types of substitutions which are possible, the 3 positions, that is ortho, meta and para positions. It has been found that when you have a monosubstituted benzene, this group causes the substitution, the second substitution will have 2 possible outcomes. I told you there are 3 possible structures or positions, that is ortho, meta and para substitutions. But it has been found that the group that is already attached, the substituent that is already present, causes 2 behaviors. One behavior is where the group has such an influence on the incoming group that it either substitutes at an ortho position or at a para position. It does not substitute on a meta position. Right? So, one kind of behavior is seen that some certain types of substituents, they affect the second substituent in such a manner that the second substituent can only attack either the ortho position or the para position, not the meta position. And the second is that there are certain kinds of substituents which, if present, they will not let the ortho and para substitutions occur. They will only encourage meta substitutions. So the presence of one substituent is kind of giving a direction to the second incoming group. It is as if, one student has already come into the class and there are other children who are walking in, and that person kind of assumes a leadership role and he tells, okay, if you're coming, why don't you sit here? You sit there. You sit there. He's giving them positions. So that is the kind of influence that the substituent, the first substituent, has. It directs the incoming groups either to the ortho and para position, that is one category, and there are other types of groups who do not like the ortho and para position. They say no, go and attach on the meta position. So accordingly they are said to be two types of substituents: the ortho and para directing groups and the meta directing groups. Groups which are substituents which are going to direct the incoming substituent either in the ortho and para position, and then there are a second category of groups or substituents who direct the incoming group or substituent to the meta position. Now that this is clear, let me first read this. The nature of the first substituent. Now, who decides? How is it decided that whether a group would be ortho and para directing or would it be meta directing? It is the nature of the group which decides whether it will be ortho and para directing or will it be meta directing. While I explain this, it will become clear to you which groups are the ones that are ortho-para directing and which are the groups which are meta directing. So the nature of the first substituent causes two types of behavior: ortho and para directing or meta. So you either get ortho and para products, or from the substituent you will get only meta product. One of the two. It cannot be ortho, para and meta, all three. It will either be ortho and para, one category, and the second category is only meta. So this is known as the directive influence, the leadership role, direction. He's giving direction to the incoming groups. Excuse me. So what are ortho and para directing groups? As you understand, the groups which direct the incoming group to ortho position and the para position. Ortho position is these two positions, or the opposite position, the para position. So groups that will allow the substitution only at ortho positions or para position are said to be ortho-para directing groups. So groups that direct incoming group to ortho and para positions are called ortho-para directing groups. If we take the example of phenol and understand why these groups are ortho and para directing, and what is this nature that we are talking, what is the nature of these groups that makes them ortho and para directing? If you look at phenol, phenol is present in these resonating structures. Phenol is not just one structure. The lone pair of electrons present on oxygen, it kind of participates in the resonance, and therefore you have these resonating structures of phenol. Let us see what happens. In the first structure we have OH, the phenolic group, that is alcoholic group, attached to one carbon with a single bond, and there are two lone pairs on oxygen. One of these lone pairs shifts and forms a double bond with this carbon. As soon as it forms a double bond, we know carbon cannot form more than 4 bonds. And it already has formed 4 bonds, 2 with this carbon, 1 with this carbon and 1 with oxygen. So as soon as the lone pair makes a double bond here, the double bond, the pi electrons here, they are forced to shift away because carbon cannot form 5 bonds. Carbon is a very small atom. Forming 4 bonds also really saturates it. It cannot have any more electrons. Therefore, it pushes the pi electrons away from itself. When it pushes the pi electrons away from itself, a negative charge occurs on this carbon. And this carbon, since it does not have a proper bond, it has a lone pair of electrons and the negative charge comes here. Now, the molecule does not like negative charge running up. It would rather form a bond. So what happens? This lone pair here now pushes on this side and tries to form a bond here. As soon as it forms a bond here, this carbon now has 5 bonds and it cannot tolerate 5 bonds. So the pi bond here, the 2 electrons of the pi bond are pushed to this carbon. So now this carbon has a negative charge while these two have formed a bond here. As soon as oxygen gave its lone pair, oxygen becomes positively charged. So you have positive charge here. While the negative charge is now jumping around. So we say the negative charge is resonating while the positive charge is static. The same thing happens. These 2 electrons now try to form a bond. So they shift to the next bond and they form a pi bond here while the electrons of this pi bond are pushed back here and they form a bond here. Since they are pushed up here, you get the negative charge here and the bond of this these 2 electrons, they form a bond here. As soon as the negative charge comes here, the negative charge pushes itself to this bond and you get a bond here and I rubbed against the board. So all of it is kind of a little blurry now. Anyway, so we find that this benzene ring now, if you see the first structure and the third structure, they are identical. This bond again goes back, the lone pair goes back to oxygen, it becomes neutral, there is no positive charge, and since you have all bonds, there is no negative charge also. But the position, these two are different because here you see the double bonds are here, here and here, but here the double bonds are in those positions where they were single bonds in this structure. So they are kind of Kekule structures of each other. So these are the resonating structures of alcohol, also of phenol. Now how does this make it ortho-para-directing? After understanding these structures, what do we see? Why do we say it is that phenols are ortho, if it is the phenolic group is ortho and para-directing, or the OH group is ortho and para-directing? If you notice in these resonating structures, the negative charge, where was it? The negative charge is on the ortho position here, it's on the para position here, and it's on the ortho position here. So whenever a substituent comes towards benzene, it always looks for the electron-rich site because it is electrophile. It is attracted to electrons. Since it is attracted to electrons and the electron density is more on the ortho and para positions, therefore, whatever substituent comes will come and attach itself to the ortho and para position. Right? So that is why phenol, the alcoholic group in phenol is ortho-para-directing. That is why it has a directive influence, because as you see in the resonating structures, the negative charge is going to be present on the ortho and para positions. There is another thing, another effect that is seen here. You have studied about these effects in organic chemistry, some basic principles and techniques. I have explained all of these in that chapter, and I would encourage you to really do that chapter thoroughly to have your bases very strong. There is another effect. Oxygen is more electronegative than carbon, much more electronegative than carbon. So oxygen has a tendency to pull a shared pair of electrons towards itself, which causes polarity in a molecule. You know about this. Whenever one atom is in two covalently bound atoms, if one is more electronegative, it has a tendency to pull the shared pair of electrons towards itself, making the molecule slightly partially polar. This effect, in the case of hydrocarbons, is shifted to the next carbons also, because as soon as the electrons shift towards one atom, this atom becomes slightly deficient in electrons. So the next atom pushes its electrons towards this. So kind of, this was deficient in electrons, it pulled electrons. This becomes deficient, it pulls electrons from the next member. That becomes deficient, it pulls electrons from the next member. This is known as inductive effect. The effect is induced in the neighboring carbon atoms. So oxygen, being more electronegative, has a -I effect, negative inductive effect. Negative inductive means that negative means is minus negative. It attracts electrons towards itself. Being more electronegative, it attracts electrons towards itself, which is opposite of what we were seeing in ortho and para-directing group. We wanted oxygen to give electrons to the ring so that the electrons would become more, the density of electrons would increase at the ortho and para positions. But the minus I effect of oxygen is acting in opposition to the resonance effect. So, since it is acting, although it is acting in opposition, it is pulling the electrons away from the ring. If you really see, the OH, what it did by giving this pair of electrons, what it did, it made electrons or negative charge increase in the ring. So, it is an activating group, it is an electron donating group. Yet, due to its minus I effect, it is an electron withdrawing group. You see, it has both the behaviors, but the electron, since lone pair of electrons, when they move and the negative charge is so pronounced and properly moving in the ring, this effect is stronger while the minus I effect is weaker. So although that minus I effect is kind of deactivating the ortho and para positions at the same time, yet it is the resonance effect which is more pronounced, and that is why this is an ortho-para-directing group. Whenever there is a tug of war, if the pull on one side is more and the pull on the other side is less, obviously the win will be of that team which is pulling more. In this case, these two effects, they cause a kind of a tug of war. The minus I effect is deactivating, but the resonance effect is the use of these electrons is activating. But the activating effect is stronger, therefore on the whole it is this effect, the resonance effect, which makes phenol an ortho-para-directing, or the OH of the phenol an ortho-para-directing group. So let me just read this now. Why do we see this? Why is phenol ortho-para-directing? This is because the electron density is more at the ortho and para positions, which I explained to you, in these resonating structures. Now you have to note that minus I effect of OH group will cause electron density to reduce at ortho-para positions. Yet the overall effect is the increase of electron density. Oxygen is pulling electrons, yet oxygen is also giving its lone pair of electrons. So this effect, the total giving away of the electrons, that effect is stronger. Therefore, on the whole, the OH group is ortho-para-directing. Yet overall effect is increase in electron density, and therefore these are the OH group is ortho-para-directing. Other activating groups or all activating. Now since they are causing the electron density to increase in the benzene ring, they are called activating groups. If a group pulls the electron density away from the ring, it is said to be deactivating group. So the OH group is activating group because it is increasing the electron density in the benzene ring. Other such groups which are activating groups and which would be ortho-para-directing are NH2, NHR, OCH3, NHCOCH3, CH3, C2H5, etc. If you look at nitrogen, it has a lone pair of electrons. NHR, it would have a lone pair of electrons. Oxygen has two lone pairs of electrons, we saw here in OH group also. NHCOCH3, again nitrogen has a lone pair of electrons. So all those atoms which have lone pair of electrons which can be made available to form this double bond will be activating groups. And if they will be activating groups, they would be ortho-para-directing. Right? Now, why did I leave out methyl group and ethyl group? In the case of methyl group and ethyl group, these are carbons and the benzene ring also has carbon. Yet they are ortho-para-directing. What would be the cause of this? What could be the cause of methyl and ethyl group being ortho and para-directing? in these cases, carbon does not have a lone pair of electrons. It has only 4 electrons and it is already forming 4 bonds, both in methyl and ethyl group. 1 bond with the benzene ring and 3 bonds with hydrogen. Here 1 bond with the benzene ring, 1 bond with hydrogen with another carbon, and the other 2 with the 2 hydrogens. If you see the carbon which is attached to the benzene ring. Now carbon does not have any lone pair of electrons, so such a situation is not seen, where carbon can donate a pair of electrons to the ring and thus become the electron donating group. Yet methyl and ethyl groups, they do donate electrons. How do they do it? By another effect which you have studied in the previous chapter, which is hyperconjugation. So alkyl group, they have, okay, since it is carbon, it has a plus I effect. It has plus I effect. It pushes electrons away. The methyl group, it is not more electronegative. Therefore, it does not pull electrons towards itself. Rather, it pushes electrons away from itself. It has plus I effect and it shows the hyperconjugative effect also. Hyperconjugation also occurs in the case of methyl and ethyl groups. Let us study how hyperconjugation occurs. Let me just clear this up and show you how the hyperconjugative effect is seen. Let's turn this into the methyl group, okay? And let me show You've studied in hyperconjugation that the only difference that is going to happen here is the change in the group. C. Okay. Now, carbon, hydrogen, hydrogen, and hydrogen. Okay? Carbon, hydrogen, hydrogen, and hydrogen. I'm not making one bond here, I'll explain to you. Hydrogen, hydrogen, hydrogen. Carbon, hydrogen, hydrogen, and hydrogen. Carbon, hydrogen, hydrogen, and hydrogen. So, this is the methyl group. If you look here, what happens? What is hyperconjugation? In hyperconjugation, when you have one of the sigma bonds, when you have pi electrons in conjugation means alternation. When you have pi, this carbon, the adjacent carbon, if it has pi electrons, then hydrogen, which is the sigma, the electrons of the sigma bond between carbon and hydrogen, they kind of can get displaced. They can participate in the conjugation and they can participate in resonance. This is a special effect. And what happens? This sigma bond breaks. And when it breaks, it results in the formation of a double bond here. And if it breaks, if this bond breaks, it forms a double bond here, a positive charge. This hydrogen would have a positive charge. The hydrogen is not bound to carbon, yet it has a positive charge. But since this part of the molecule is negatively charged, the hydrogen does not run away. It stays there. So this effect is known as hyperconjugation, which causes the increase in electron density in the ring in the same manner. You will again have the electron density more at the ortho and para positions. Let us see how. The moment the double bond is formed here, this double bond, the electrons are pushed to this carbon and therefore this carbon becomes negatively charged. As soon as that carbon becomes negatively charged, the negatively charged pi electrons move here to form a bond and the electrons of this bond are pushed to the para position. So negative charge collects at the para position. Now this pair of electrons forms a bond here and the pair of electrons here, they come here and form the negative charge collects here. This negative charge then moves here to form the bond, and as soon as this bond is formed, the two electrons of the hyperconjugation, they are returned to the hydrogen and hydrogen gets back its electrons and becomes bound to form the methyl group. So even if the methyl group did not have the lone pair of electrons, one of the a pair of electrons from the sigma bond participates in resonance, thereby activating the group. Right? And that is the reason why methyl group is also activating. Right? Another thing, it has plus I effect. The methyl group, it has a tendency to push electrons away from itself. The reason being that carbon is a very small atom, as I told you, and these 8 electrons which are around, it forms 4 bonds in a methyl or an ethyl group. Even these 8 electrons are really a large number for the little carbon atom, and therefore it tries to push. There are too much negative charge too close. So it kind of pushes electrons away, and when it pushes the electrons away, it has a plus I effect. And plus I effect also increases the electron density on the ortho and para positions. So both of these, plus I effect and hyperconjugative effect, in the case of methyl and ethyl group or the alkyl groups, they make them activating groups or ortho and para directing groups. Right? Is that clear? So ortho and para directing groups. Which ones are those? Either those which have lone pairs of electrons on them, or which have an effect which is going to cause an increase in the electron density in the ring, or they are activating groups. So that was ortho and para directing groups. Let us now start with the second. Oh, there is a little more before I move on to the metadirecting groups. In aryl halides, if you had a halogen here, there is again a problem with aryl halides. Halogens are, in comparison to oxygen, halogens are even, chlorine would be even more electronegative. So if halogens are there, they are quite electronegative, and therefore they have a minus I effect. The minus I effect will be strong, and therefore they would be deactivating groups at the ortho and para positions, just like oxygen in the case of OH, that is phenol. But halogens have 3 lone pairs. They form 1 bond with carbon, but they have 3 lone pairs. Therefore, the chances of donating any of these lone pairs to form the double bond and therefore activate the group at ortho and para positions is greater in the case of halogens also. So we say in aryl halides, halogens are moderately deactivating because of minus I effect. So overall density on benzene ring of electrons should decrease, and it decreases due to that effect, and making further substitution difficult. But due to this resonance and due to those electrons which it can give, due to this resonance, it still has ortho and para directing. It still shows ortho and para directing behavior. That is the case of that is benzene, the aryl halides, haloarenes. So the electron density is still more on the ortho and para positions. Therefore, although you would expect halogens to be deactivating because they are moderately deactivating, yet they show ortho and para directive influence due to the number of lone pairs it has and its participation in resonance. Now we come to the second category, that is metadirecting groups. So whatever we studied about ortho and para directing groups, the opposite of that would be true for metadirecting groups. What did we say? They have electrons, lone pairs of electrons, which can be donated to form the double bond with carbon. These would be groups that do not have lone pair of electrons. They have a tendency to pull electrons away from the benzene ring. Or when you say the electron density in the benzene ring is increasing, it is activating, then if the electron density is decreasing, it means these groups are deactivating, right? So metadirecting groups, groups that direct the incoming group to the meta position. One. Well, how would you define them? Metadirecting groups are groups which are present and which direct the incoming substituent to the meta position, not at the ortho and para positions. These are electron withdrawing. They will pull electrons away from the ring and therefore they will be deactivating. So incoming group to meta position. Examples of these are NO2. Now you will say, I told you here that all of these groups have NH2, NHR, OCH3. I told you NHCOCH3. They all have nitrogen, and I told you since nitrogen has that lone pair in these structures, therefore that lone pair can be used to form the double bond, and therefore they provide that pair of electrons to the ring and increase the electron density in the ring. And the first example we take here is NO2, which is also nitrogen. Then why is this not activating? Because of the structure of NO2. In nitrogen, the lone pair which is present is already used up to form a coordinate bond with oxygen. It is already used up to form a bond with oxygen. Therefore, a lone pair of electrons is not available at nitrogen to participate, to be in conjugation with the electrons in the ring, and they cannot be contributed towards the ring. So the lone pair is already used up. Then CN group, CHO group, COR group, COOH group, COOR group, and SO3H. In all of these, the atoms, either the atom itself or the atom next to it, is pulling the electrons away from it, and therefore the atoms cannot contribute, cannot give electrons towards the ring. They are electron withdrawing groups. So examples: NO2, CN, CHO, COR, COOH, COOR, SO3H. All these are groups which are electron withdrawing groups. They are deactivating groups. And in the case of NO2, the nitro group, let us see that now. It also has resonance. And let us see the resonating structures of nitro group. Now in NO2, nitrogen is present here. Nitrogen is connected to the carbon of the benzene ring, and there is one coordinate bond with oxygen and a double bond with the other oxygen. This oxygen has two lone pairs. Now what happens that since it is an electron withdrawing group, it pulls electrons from the benzene ring. Nitrogen is using its lone pair to form a bond with oxygen. So it is deficient in electrons. So it pulls the pi electrons from the benzene ring. When it pulls the pi electrons from the benzene ring to form a double bond with nitrogen, nitrogen cannot form so many bonds. So one of the pi bonds between this oxygen and nitrogen, it breaks, and the two electrons go to oxygen, making three lone pairs on oxygen, and oxygen becomes negatively charged because one of the electrons was of nitrogen. Nitrogen becomes negatively charged, but since these pi electrons have moved away from here, this carbon to which one electron belonged, it becomes positively charged. When it becomes positively charged, the pi electrons present here try to help by shifting the bond here. When it shifts the bond here, this carbon also gets its electron, but this carbon now becomes electron deficient. And that is what we see. When it becomes electron deficient, it acquires a positive charge. Now, at NO2, the oxygen is negatively charged and there's a double bond between nitrogen. That part is satisfied. But the ring is undergoing a resonance of the positive charge. So, now this becomes positively charged. So, this pair of electrons of the pi bond, they jump this side and they form a bond here, and the positive charge now shifts to the ortho position. It shifts to this place. And in the next step again, when this is in this place, the double bond here again tries to shift back here to satisfy the positive. Therefore, the bond forms back here. The pair of electrons here shifts back to here, and it forms the double bond, and the original structure with just the shifted double bonds, you get the Kekule structure of the first structure. So what did we see in this case? We saw the opposite charges. The same kind of action is occurring. There are electrons which are shifting, but here the electrons are shifting because they have to fulfill a positive charge. And what is moving is the positive charge. In the ring, what is moving is the positive charge, not the negative charge. And when an electrophile comes, it is not attracted to positive charge. An electrophile itself is positively charged. So it will be repelled by positive charge. And where is positive charge? Positive charge is on the ortho and para positions. So obviously when the positive charge is on the ortho and para positions, the positively charged electrophile that comes cannot attack at ortho or para positions. The only position that is there which is available is the meta position. Therefore, the second substituent that comes cannot attack ortho or para positions because they have positive charge, and therefore the only positions which are kind of comparatively more electron rich are the meta positions. Therefore, the incoming groups come and attach to the meta position, thus making them meta-directing groups. Clear? So when a group is deactivating, it has an overall tendency to pull electrons away from the ring. Then the substitution will occur at the meta position. Not because electron density has increased on the meta position. No. It is just because the incoming group has no other option. That is the only option it has. Meta position, because ortho and para positions are positively charged. And the electrophile will be repelled by positive charge because electrophile itself is positively charged. So now, deactivating groups. The electron density at the ortho and para positions is comparatively less than that at the meta position. The electron density is less because it is positively charged. Obviously, it is deficient in electrons. So, and the electrophile is also deficient in electrons. So, since the electron density is less at ortho and para positions comparatively than the meta position, the incoming electrophile will attack the comparatively electron-rich meta position. The incoming group will come and attack the meta position, which is in comparison to the ortho and para positions, at least it is not, it may not be negatively charged, but at least it is not positively charged. It still has more electrons than the positively charged carbons. So this was directive influence of monosubstituted benzene. Now, the last topic of this chapter is carcinogenicity and toxicity. Since I want to make this the last video, let me just mention that that's not an extensive topic. You know, when benzene rings fuse together to form larger molecules, giant molecules with benzene rings, they tend to act as carcinogens. A carcinogen is a compound that is that causes cancer. And since it causes cancer, it is toxic. When you burn petrol, when you burn tobacco, when you burn coal, and the oxygen is not enough, when these substances, they burn in insufficient supply of oxygen, you get giant molecules, fused benzene rings together to form giant molecules. Whenever you have these giant fused benzene rings together, they act as carcinogens. That is the only thing to be known here. You can see some of the structures of the carcinogens, and the knowledge of that is enough. And why do they act as carcinogens? These molecules are giant molecules, and when you inhale them through tobacco, or when these petroleum and coal are burnt, when you inhale them, they go into your system. They can go and get attached to the DNA of your cells, and they can alter the DNA. And once the DNA is altered, the mutations can cause uncontrolled multiplication of the cells, which is nothing but cancer. So this was the chapter, and with this video we come to the end of this chapter. If you want to watch other videos of this chapter, click the link, the video that appears on top of this video. And if you found this video helpful, give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.